and it is the transitive closure of R. We can construct R star by combining all power of relation R. So this is union. Then we basically union all power N over R. Transitive closure is quite complex because, say, if you look at this relation R2, which consists 1, 2, 2, 3, 3, 1, you may think that, okay, we have 1, 2, 2, 3, so you need to add 1, 3. And 2, 3 there, 3, 1 there, you need 2, 1. That's, if you think that are all that you need to add, you are wrong, because after you add 1, 3, okay, after you add 1, 3, you need 1, 1 because 1, 3 and 3, 1. Okay, you need 1, 1. So what I mean here is that when you add things into the relation, you may need to add subsequent element. Okay, so things become complex if there are 100,000 of relation instances. Okay, and in when we do a lot of planning for road scheduling or a trip to visit city, we can use relation to stand for a road between two cities. And if you want to calculate the transitive closure on your trip to visit every city, then it could be very complex if there are many cities as well. ครับอะไรนะฮะพอ33นะฮะอ๋อ33ใช่ต้องมี3113ใช่ไหมฮะถูกต้องมันต้องการโอเคดีเลยครับเราจะได้เลคเชอร์ที่ correct มากขึ้นดีมากครับดีมากผมเวลคัมคอมเมนต์ทุกอย่างเลยนะฮะนะครับเพราะว่าเรามี3113ใช่ไหม so we need what 33 you see very complex see not just easy not easy. Now we come to the probably the last part on relation. Relation is very good. We can use relation to order things. Okay, we have a set of element S. Okay, we have a relation on set S. Our relation can be used to create structure on elements in S. We are interested in special kind of structure called partial ordering. A relation R is called partial ordering if it satisfies three properties: reflexive, antisymmetric, and transitive. These are examples of relation which can be used to do partial ordering. Okay, you can see them: division, subset, less than, equal, and so on. Let me show you two examples. The first one is the less than or equal relation on the set of integers. It is partial order because it has these three properties. Okay, to understand antisymmetric better, maybe this one will help you. Less than or equal. It is not symmetric, right? Because if y is greater than x, it's not true that x greater than equal to y, right? It's not symmetric, but it allows reflexive. So this is example of antisymmetric. Similarly to subset relation, it is also antisymmetric. It cannot be that two sets are subset of each other. It cannot be that, except that they are the same set. Okay. Then exactly that means antisymmetric because it allows reflexive. Okay. So I would like to show you some example, but let me see, or it will be quite long. But let me just quickly, take you to some example. This is a partial order on subset. At the bottom we get empty set. Here we have a set which one element A, and so on. If we draw the ordering between those sets, by subset relation, we get this order. Okay, and we are interested in the structure on the relations. We come back to this later on, but let me take you back to this. Okay, why is it called partial order? This is because in partial order, if you take any two elements from the set, there may be no relation between them. For example, these two subsets, okay, have no relation on subset. Okay, partial order means you cannot. There's no strict total order. It's not necessary that you can order between the two. Okay, the set S together with the relation, which is a partial order, called a partially ordered set or just pose set. Okay, we shall just call it pose set. Then we know that it means a partially ordered set. This is the first example on partial order. We have a kind of ordering called lexicographic order. In dictionary, many words in dictionary are ordered in this style, lexicographic. But in our example, a word consists only of two characters, A1 and A2. This is one word. This is another word, consists only two characters. When we order words in dictionary, it uses this rule. The first word comes before the second word if and only if the corresponding character come before each other. Okay. Otherwise, if they are the same, then we consider the next character. Okay. This ordering, well, this is less than, right? But we talk about less than or equal. Then we have reflexive here as well. So this less than or equal, this one, not the ordinary less than, right? This one that we define is partial order, reflexive, antisymmetric, and transitive. Okay, we involve a lot of partial order in daily life without knowing. There is one diagram. Maybe I can even. Oh, okay. Yeah. That is even better, right? Okay. You can see bigger. So there is one diagram which helps us to illustrate partial order in an easy way. That is called Hess diagram. Okay, in Hess diagram, if you can see clear a little bit, in Hess diagram we remove the reflexivity relation and transitivity relation to get a simplified view of partial order. So this loop, okay, this loop represents reflexivity property. We know already that partial order must be reflexive. There is no point to draw it, okay, because it's so complicated. We remove it, okay, to get a simple look at the relation. And we don't need transitive because, for example, 1 to 3, okay, 3 to 6. Then by reflexive, we got to have a line from 1 to 6. Well, we know that we don't need this because we already know that it is partial order. Automatically, we know that if we can go from 1 to 3, 3 to 6, we can go from 1 to 6. No problem about that. There is order between that anyway, so we can remove it. This is the Hess diagram for division, okay, divisibility between elements in this set. Okay, if one can, the bottom element can divide the upper element. Okay, for example, 1 can divide 3, 3 divide 6, and so on. So we normally draw the Hess diagram. The Hess diagram is